Saxon Advanced Mathematics, lesson 125. I'm just back from the drugstore. I ran up and got batteries so that I can continue this lesson. We're on example 125.2, and we're in the process of entering these two functions. But before we do that, what we want to do is zoom in and reset our windows to the standard size. So I'm toggling down through this list till I get to number 6, which is standard. I'll enter that. That will give us our nice basic grid. Oh, and the one of the functions is already in there, so it's graphed part of it, but that's okay. I'm going to check window, and I can see that my graph is set to go -10 on the minimum side and +10 on the maximum side. That's a nice normal setting, so we're good with that. So now we're ready to go to our list of functions here at y equals. There's the first one that I entered from last time. And now for the second one, I want to enter x plus 1.44. So there's my x key plus 1.44. Okay, so now I have both of my equations entered. And we're going to try the old trace method one more time, and then we're going to do the new way. So trace, and there it is. Those are my two equations graphed. And if we use the tracing function, then what we're doing, let's see, where's my cursor? There it is. So I want to creep that up. And you can see here, it just doesn't give me a really strong intersection point. Right? I can zoom along, and I'm trying to get that cursor to land right on the intersection. That's about as close as I can make it land. And I'm just comparing my values to what John has. This is what John considers to be the best approximation of that intersection. It is x equals 1.702, 1277. That's this number. I'm reading it out of the book, and you can see it here. And then that gives us a y value of 14127. No, that's a different. That is a different y value. Okay, so what I can see is that this trace method is not giving us the best approximation of that intersection. So I want to go to calculate. Notice that's in yellow, so I do second, and then I hit that button. And then this gives me the different options of what the calculator can calculate for me. I want the intersection. So I toggle down to 5, where it says intersect. Then I hit enter. Now what the calculator does is it doesn't just depend on me clicking that little cursor along. It does the actual calculation. And it says that, it wants me to confirm a couple things right now. It wants me to confirm that I'm on the first curve. So what I do is I toggle up a little bit and I say, yeah, that's the cursor's on the first curve right now. That looks good. So I hit enter for yes. And then it says second curve. So then I just check and make sure I'm on the second one. Yeah, see how I'm moving up the line? That means I'm on the second one now. So I can hit yes for that. Guess. Okay, now I give it my best shot of where I think that intersection is. And I think it's right about there. So I hit enter again. Now it uses my approximations to come up with actual values for that intersection. So we're no longer relying on my ability to toggle in carefully. We're relying on the calculator's ability to actually calculate it. And let's see what the values are. 1.6201, and I didn't say it right. It's 1.6281064. That's exactly correct. And the y value in the book is y equals 3.0681064. That's exactly what we got. So Using the calculate function is always the way to go because it takes all the guesswork and all of my ability to toggle into the right place. It takes that out of the equation. All I have to do is confirm which is the first curve, which is the second curve, just to make sure that the calculator's just saying, you know, just double check my estimating here. And then we give it our best guess, and then it actually calculates the precise answer. So the trace function is not our friend. We don't want to use it. We want to use calculate. So that's the answer. These are the x and y values at which those two functions, which we wrote here, at which they intersect. And we could write them down. In fact, I'll just round them. Just a second. This is bugging me that I didn't do this. The place where these intersect is at x equals 1.63 and y equals 3.07. That's rounded to the hundredths place, but that is that point, which we can see. A high 1 and a low 3, that looks exactly right, doesn't it, based on the grid? Okay, beautiful. So there we have we've solved a system of equations. We found the intersect. So in the first one, we found the turning points, right? The point at which the curve went up or down. This one, we found the intersection. Here we used the trace key only. Here we used first the trace key, and then we used the calculate key and got the exact values. So we're happy with that. In our next problem, we're going to find some roots, or what we would call zeros. So this is the way the problem looks. It says find the roots of the polynomial equation, and then here we go. X cubed plus 4x squared plus x minus 4 equals 0. This looks, no, it's a different problem. I thought it looked a lot like the problem in the first example, but it is slightly different, right? That's a minus 6 and that's a minus 4. Otherwise, they're very much the same. We want to find the roots of it. We want to find the x equals. So when we graph it, it's going to be, we're looking for the place where this graph crosses the x-axis. That's what we're looking for. P.S. I want to tell you that the instructions that John gives in the textbook as to how to find these things actually work precisely. We've never really relied on John's calculator instructions because we've been using the smart calculators on our phones that operate slightly differently, but John has written all of his instructions for T81s, 82s, 83s, and so this is right on. Okay, so what we're going to do is clear out, we'll go to our x values, we're going to clear these out because we want to start with new ones. Okay, so we'll go back to our first function and we're going to enter this. So it is, I'll hold it up here so you can watch me enter it. There's our x key, and then we want to raise that to the third power. And then we're going to add 4x squared. For the x squared, we can just use, did you see what I did? I used this to enter the x, and then this one to square it. So now we have 4x squared plus x minus 4. We use this one for the operation of minus. We use this one just to switch the value of a number. Okay, so now I've entered it. That looks good. Now we want to enter, we don't want to do trace. We want to do calculate right there. So it's second trace. And then this gives us lots of options, again, for what we want to calculate. Value, 0, minimum, maximum, intersect. We want to find the zeros in this case. The zeros are, for practical purposes, zeros and roots are synonymous. So we're going to hit the 0 key, and we're going to enter it. There is our beautiful picture. Now, in order to help the calculator hone in on these values, we have to give it some hints, just like we did last time. So the first question it asks us is for a left boundary. So what we do is we use the cursor, and we're going to start with this, this first 0 all the way over here. We're going to help the calculator do this. So we're going to find any point to the left of this point where it crosses the x-axis. So this is one. This will work. This is a left boundary, so I enter it. Then it asks me for a right boundary. So I'm going to go up. Now I'm on the right side of the boundary. I try to keep it relatively close to where I know that 0 is. I don't want to go around the top of that curve. I want to stay fairly close. There's my right boundary. I hit that, and then my guess. So I'm going to go back and try and put it as close as I can. Those are the two options. I like that one better, so I'm going to enter it. And it says that that 0, the first 0, I'm going to write it down on my paper. He tells us that the value of that far left 0 is x equals minus 3.342923. Sorry, I'm having to tip the calculator so I can read it. And that is the correct answer. Okay, so we followed the little prompts here that said click a point on the left boundary, click a point on the right boundary, make your best guess, and then it calculated the exact value of where the line first crosses the x-axis, the leftmost boundary. Now that we've established this one, we're going to go back, working our way toward the right. We're going to do the same process to get the value of this point, which is another one of our zeros, and then we'll do the same thing for our third crossing point over there. So I use my cursors, where did my toggle go? I have to go back to the calculate. I re-enter that we're looking for a 0. This time, when I go, my left boundary will be above the curve, right? It's wherever the line we're looking at, whatever is to the left of our point of intersection. So this will work. I'm going to stand up so you can see it better. That little X, the cursor, is to the left of the place where the line crosses the x-axis for the second time. So this will work. Now it wants a right boundary. So I keep going along until, again, I want to be clearly on the right side of that point, but I don't want to get mixed up in this lower turning point. So this will be a good one. Then it wants my best guess. So I'm going to toggle back up. I think that's the best guess. So I'm going to enter that. And it gives me another value. It says that this 0 is minus 1.470683. All right, cool. X equals minus 1.470683. Beautiful, and now we will repeat the process. Second calculate. We're looking to get a 0. And now this time, again, it's left boundary, but this time we're talking about this third point of intersection. So now, again, I have to think carefully. What's on the left side of that point? Well, the curve is kind of gently drifting toward the right. So below the line is my best guess. Is a good left boundary. Then I need a right boundary. Notice how the screen is prompting me, so I don't have to remember all this. And then my guess. Which one's the best? That looks like it's the closest. It calculates, and it tells me my third 0 is at 0.8136 blah, blah, blah. Let me copy it down here so you can see it. X equals, I'll add the 0. The calculator doesn't show the 0. So it's not necessary. And there it is. And so these are the 3 values. These are the 3 roots of that big bad polynomial we had at the beginning. And we can see that the zeros match up to the places where the curve crosses the x-axis, right? So there's 1, 2, 3 places where it crosses, and these are the values of them. That represents the zeros or the roots of the equation. Beautiful. This is the right answer. Okay, so we're not fooling around with that trace button anymore, just to be clear. That was great, but calculate works much better. We still have to give the calculator a little help to kind of hone in, but it calculates a precise and exact answer for us. All right, I think it's one more problem. It's one more problem. Are you ready? This is the last problem in the book. 125.4, use the graphing calculator to find the zeros of the polynomial x squared plus 1. Okay, so again, we haven't set it up to be this way, but we know that we can look at this as a function where y is equal to. So let's go back out to our functions. Let's clear out the old one and let's write the new one in. We enter the x and then we use the x squared plus 1, right? And we want to calculate, no, first, yes. We want it says to find the zeros. So we'll go right there to our list, zeros. Now, when we look at this picture, we notice something odd. Remember that zeros represent the place where the curve crosses the x-axis. Is this curve crossing the x-axis? It's not. So based on the picture, we say, hey, wait a minute. It looks like there are no zeros to this, which is another way of saying there are no roots to this, which is another way of saying there's no solution to this problem. And we think, now wait a minute, how can that be? Let's lay the calculator aside and use our computational brains again and see if we can solve for what the roots might be. And what we realize, here's our thing, x squared plus 1. We realize that this can only be broken out as x plus the square root of minus 1 and x minus the square root of minus 1. We're thinking of this as a difference of 2 squares, right? And so this is like a squared minus b squared. And we know that this factors into a minus b times a plus b, right? So we're sort of forcing this into a difference of 2 squares format, but the only way we can make the difference of 2 squares works is to say that this square is minus 1, right? So we say square root of minus 1, square root of minus 1. This is kind of a weird idea, but basically what we're doing is we're taking this and we're forcing it into this factoring pattern. In order to do that, we have to turn this into a minus 1. That means that if we do the algebra on this, we would solve it for x equals plus or minus I, right? Because here, let me just show you an extra step. This would be x plus square root of 1i equals 0, or x minus square root of 1i, right? Because square root of minus 1 is the same thing as I, square root of 1 times I. Square root of 1 is 1. So this then becomes x plus I equals 0, or x minus I equals 0. And then this we can write as x equals plus or minus I, which is what we had up here. I just showed you a few more steps to help your brain see how we got from here to there. So what that tells us is that the only roots of this original, Grace wants to go outside and she's crying. The only roots of this are imaginary numbers. There are no, she's now trying to wedge my hand up off my paper. Good girl. You have to hang on just a minute longer. We're so close to the end. Hang on, hang on. There are no real roots to this problem. We can solve it using pencil and paper. And we see, oh, this is the reason why there's no real roots. And that's why, when we look at our picture, it never touches the x-axis. Our curve never touches the x-axis because there are no real roots. And the real roots would show up in the picture, but there aren't any. And that's why the picture doesn't ever touch the x-axis. And I love this problem for one simple reason, and that is that sometimes, all the time, your brain and the calculator have to work together. The calculator helps us by taking some of these calculations out of our hands and doing them quickly for us, but we still have to stay mentally engaged in what is happening because sometimes we need our full math brain and our calculation power to make sense of an answer. Oh, it cleared out. Sad. There it is. This answer doesn't make any sense until we stop and do some calculations and go, oh, wait a minute. Based on what we calculate here, the only roots are imaginary, which means there are no real roots, which explains why our curve never touches the x-axis. I love this as our last problem because it is such a great illustration of the relationship I want you to have with your calculator. Yes, use it. It's going to save you a lot of time. It's going to give you a lot of information that you don't have to grind through. But we can never just sit back and put our feet up and let the calculator do all the heavy lifting. We have to constantly be interpreting the results, making sure they make sense, supplementing what we find on the calculator with our own calculations when necessary to interpret them properly. So don't ever think your calculator is going to do all the work for you. It's not. But guess what? That is the last problem in the last book. And the only thing I have left to say to you is, congratulations, you made it. I enjoyed studying with you. I hope everyone in the world loves their job as much as I love mine because nothing to me could be more fun than teaching you math. But that time has come to an end. Please reach out to me at any point in your math career if you have any questions or problems or things you want to bounce off me. I am here to serve you with your math needs forever. So, thank you for studying with me. Good luck to you in the future, and goodbye.